Nice to meet you. Yeah, hello. My name is Jaeyoon Jung, software engineer from LG Electronics. I'm pleased to have you in my session today. So today, before starting my presentation, I'll give you a short introduction to myself. I am the lead developer of webOS graphics system, and I have been contributing to webOS project for the last 7 years since my company has acquired webOS from HP in 2013. And the topic for today I prepared is also about webOS graphics system, especially how we have enabled multiple displays in webOS. Qt is one of the most important framework we use in webOS. Especially we use Qt for the graphics subsystem. And we have a well-known compositor in webOS, and it uses Qt Scene Graph as the graphics composition core. And also we use Qt Wayland for the integration between Wayland and Qt. So this event is actually the Qt WOS Summit. So I'd like to focus on Qt today, and for example, advantage of using Qt to enable multiple displays in webOS. Okay, let's get started from the introduction. This is the introduction to LSM. LSM is the name of Surface Manager in webOS, which means Lunar Surface Manager. LSM is also a Wayland compositor in webOS. So it is written in Qt and a QML Wayland compositor actually, based on Qt Wayland. And it is also a Qt QML application. It can also have some local QML UI elements as well. As a Wayland compositor, LSM is capable of handling surfaces from Wayland clients, the apps. In addition, since it also can have local QML UI elements, so it is able to composite all Wayland surfaces as well as local QML elements together. Input event handling is also one of key features that LSM provides as a compositor. And so LSM can read input events from various input devices such as keyboard, mouse, touch screens. Recently, we also enabled tablet events. And so LSM is the component that handles those kind of input events in webOS. The virtual keyboard, in other words, input method, is also one of key feature of LSM. And we have our own architecture for input method in webOS based on the Monolith project, one of open source project. I'll show you a brief architecture of the input method architecture in the upcoming slide. So in the right-hand side, I added a screenshot from the event last year. Actually, I had also presentation in Qt WOS Summit 2018 here in Berlin. And at the time, I gave a presentation about the overall introduction to LSM. So you can find my presentation material last year in the Qt website. Is about resources.qt.io. You can find it from Google, I think. You can also see the video captures in that website. So for more information about the introduction to LSM, you can find that material as well. Okay, this is the overall architecture diagram of LSM. So let me go through first from the rectangle here. So this rectangle shows the LSM process itself. So as I mentioned, LSM is one of Qt Wayland compositor. And it is also a Qt GUI application, so it requires to run on top of QPA. Other than that, we also have other blocks like here and outside of the LSM process, like Wayland protocol between the compositor and Wayland clients. And also we have Wayland adaptations for different type of applications. For example, for web applications, we have Ozone Wayland adaptation, which is provided in Chromium. And we have also Wayland QPA provided by Qt Wayland for Qt QML clients. There's another block on the right-hand side, which is Wayland EGL, which enables buffer sharing between Wayland compositor and Wayland clients. So these are the blocks that LSM is related with. And also LSM is one of webOS service. So we have Luna Bus in webOS as a IPC mechanism. So when LSM needs to communicate with other webOS components, we use Luna Bus as well. So this is a brief diagram, and you can also find this diagram in this website, webososd.org. Recently, we updated a technical document there with the latest architecture. So you can see more details regarding this diagram in that website. Okay, let's talk about the main topic, multiple displays. So there were a couple of requirements when we plan to implement multiple displays in webOS. So actually, it was needed for user experiences in vehicles. So nowadays, we are focusing on integrating webOS into automotive area. So in vehicle nowadays, there are many display devices, as you can see. For example, in cluster and the center stack, and even in rear seat, you can see multiple displays. So the first requirement was that we want to control those multiple displays using a single board. So that is the first requirement. There are obviously a couple of advantages handling multiple displays using a single board. So the first one would be the cost. We can reduce the cost for the having multiple boards. And another advantage would be that interoperability between displays. So if those multiple displays run in a single board, it is easier to implement interoperability between the displays because it doesn't need to interact with via network or some other connectivity technologies. So one other example for the advantage having multiple displays in a single board would be it is also possible to move application across displays. There's no need to communicate via network because it is actually a single OS instance. Every process are visible from the OS point of view. So it is quite easy to move on an application from one display to another. And there is only one compositor running in a board that manages multiple displays together. So graphic memory is managed by the compositor as a whole. So it is quite easy to get those kind of buffers and graphic buffers from here and there. So for the same reason, we also can achieve the second requirements, which is app can run on a display selected and also can move here and there around. The third and fourth requirement are quite similar. The input events and as well as virtual keyboard should be supported per display. So from the user perspective, even though we connect multiple displays using a single device, from user perspective, they are actually separate devices. So any user interaction should be working separately. So we have to provide input events separately on each display, and also like virtual keyboard, we should provide separately. So that is another requirement we have to implement. Okay, then let me explain how we solve this kind of requirements in webOS. So the first thing is about compositor. So compositor is interfacing the main graphics and input hardware platform. So what we need in the compositor is to support multiple physical displays. So if the hardware platform is capable of multiple displays, there will be multiple display connections available. So for example, if the underlying graphics system is based on DRM, Direct Rendering Manager, those display connections are seen as DRM connectors. So from the compositor point of view, compositor can see a DRM connector per display. So typically, a physical display can be represented by a platform screen in QPA. So in this diagram, we have multiple DRM connectors and one DRM connectors per one physical display. And the platform screens in the QPA side represent display resources and DRM connectors in this case. On top of that, in the compositor context, we need separate windows per screen. So per screens, we need one single window. So we call it in LSM, we call it as a compositor window, which represent the compositor output. So if we have multiple display outputs, like this case, we create multiple compositor windows. So one compositor window per one physical display, and make association between the compositor window and underlying platform screen, as well as display resources. So in this diagram, I explained about the architecture based on EGLFS. So EGLFS is actually the QPA we mainly use for the majority of webOS products. So EGLFS itself was capable of multiple screens, and so, but there was some a little bit insufficient things compared to our requirements. So we had to add more features. But the thing is that the architecture itself was capable of multiple screens. So for us, it was easier to implement our own requirement to handle multiple compositor windows on top of EGLFS. Okay, next is about Wayland clients. So from Wayland client's points of view, there is only one compositor running regardless of a number of displays. So it means that there is only one Wayland display connection to the compositor. So from the Wayland clients, there's no difference for creating Wayland surfaces, rendering contents, and sending or receiving Wayland events from or to Wayland compositor compared to the single displays case. But there's one difference because of the number of displays. So client needs to select which display it wants to show up. So we actually first look into the Wayland protocol, standard protocol. So there is Wayland output, which is which represent a physical display, and LSM actually is complies with the standard Wayland protocol. So it creates Wayland outputs per display. So we have Wayland outputs per Wayland compositor window. Each Wayland output has the information of the physical display associated with. But in reality, there is no specific mechanism between the Wayland surface and Wayland output. So for example, in order to assign a Wayland surface into a specific Wayland output, there is no protocol for that in the standard Wayland protocol. So we had to introduce a new concept, which is not exist in the standard Wayland protocol, which is called display affinity. So with display affinity, a client can tell compositor which display Wayland output it wants to show up. Then compositor LSM adds its surface to the QMS scene based on the display affinity value, so that the surface can come up with the display associated. even display affinity can change on the fly while the Wayland client is running. So in that case, if a client changes a display affinity from one to another, then LSM dynamically moves that surface from one QML scene to another, so that it results in that the surface can show up in another screen. So this fulfills the second requirement I mentioned in the previous slide. Okay, now so we get multiple compositor windows per display, and also applications, Wayland clients can run on a selected display as well. So in this slide, that's talking about the input events. So actually handling input events on multiple display environments is not that easy that you expect, because there's no relation between the display device and input device at the driver level. For example, if you have a monitor with a touch screen, then you plug HDMI cable and for the display connection, and also you need to connect the USB for the touch screen. But at the driver level, there is no connection between those HDMI and USB connection. It's the same for the keyboard devices. So suppose there are some keypads underneath the display, for example. So user press a keypad on a certain the display. That events from the keypad should go to the display associated with, but there's no information which keypad is related to which display, for example. So this kind of association needs to be implemented in a specific way. So we added a configuration between the display device and the input devices. Actually, in EGLFS, there is some mechanism to associate between the touch device and the specific display output. But there is no mechanism for the keyboard devices as well. And also, we wanted to add more feature, like, for example, if user plug touchscreen USB on the fly or unplug, something like that, this kind of dynamic USB device detection should be done in the same way. So we added some feature to the EGLFS to cover these requirements as well. But patch was not that big, so actually we probably, if you have some time, we are going to contribute those patches to upstream. But yeah, the thing is that the main architecture that EGLFS has is quite enough to extend our requirement as well. Okay. This is the last technical thing I prepared for today. It's about virtual keyboard. So let me talk about the overall architecture of virtual keyboard and input method architecture in webOS. So actually, when we started to architecturing input method, we actually forked Mali framework. It was one of our open source project. It was used to be very actively developed a couple of years ago. Now it's since that, by the way. There are three components involved in the architecture. The one is the app, the Wayland client that wants to show and to get some input from the input method. And the second component is the input method server, which actually translate the inputs from the app. And the third one is the LSM, which exists in the middle between the app and the input method server. So from LSM's perspective, both app and input method server, let's say IAM server, are Wayland clients. So they should belong to a certain compositor window. So basically, we run IAM servers per display, and with display affinity set. Then LSM actually can establish contacts between IAM server and client based on display affinity. Yeah, that is the way how we implement multiple virtual keyboard using our existing architecture. So so far I explained multiple display changes related to multiple displays in webOS. So some changes had to be done in LSM, but some others had to be done in Qt framework itself. The thing I would like to emphasize today is that the architecture of Qt framework itself is scalable and flexible enough to support multiple displays. So what we added on top of EGLFS or implemented in LSM is quite minimal. And so the key message I would like to say is that Qt was really helpful to implement multiple displays in webOS. But there are still some technical issues we had to solve in a specific way. The first one is the multiple keyboard devices. So as you may know, in Qt Windows system, there should be only one activated window in a single application. So for this reason, whenever we deliver a keyboard event to a certain window, if there are multiple windows, we have to make a specific window to be activated to get those events delivered. So, but if we make some changes on window activation, it also affects to some UI. For example, in Qt Quick, for example, it is assumed that the only one item can be an active focused item. So in that, for example, one implement using some highlight based on this active focus. If we change the activated window into another, that may affect it. So as a remedy for this in webOS, we modified a bit, the Qt declarative to allow a window can have an active focus regardless of its active state or not. The second issue is about the sharing properties between windows. So it is assumed that the property in a single QML engine can be shared, but it is not possible to share those property across QML engines. So only properties in the same QML scene can be accessible. But in our case, we had some use case to share some properties between windows. And also we have to make some property bindings across window. So we get this done in LSM by adding some context property in native code. There's kind of workaround we had. The solutions for this about not the right way probably. So probably we need some more better architecture in Qt framework itself. Actually, I'm expecting there might be some improvements in upcoming Qt releases. If there is no such improvements seen, probably we can suggest our approach to upstream in the future. So, okay, this is the last slide. So I prepared for a short demo with the video. So this demo, you can see multiple displays from a single device. So this demo actually shows IVI concept in the vehicle. So on the left-hand side, you can see the IVI application running. So it can be seen in the center stack in the front seat. And on the right-hand side is the display for the rear seat. So the scenario is to play contents from the front seat for the passenger in the back seat. So let's take a look at the video. So this is an IVI sample application. So same application can be seen in our booth. So if you visit our booth, you can see the same application running. So it is written in HTML5, so based on Enact framework. And if user selects some media contents from here and select rear right, for example, the content playback starts from the different screen. So this is one of example we can implement using multiple displays, even in automotive scenarios. So you can see many other examples in our booth. So if you visit our booth close to the main entrance of this building, you can see other demos with other hardware platforms as well. Okay, that's it. So probably this is my last slide today. So I've noted some important URLs for webOS OSE and as well as the github.com for the source code. So you can visit there and download the source code, and even you can build your own webOS images, which running on top of Raspberry Pi 4. Okay, thank you for listening, and maybe I have 5 minutes for the question.
I don't know if it's on.
I can hear you.
Okay, it's on. Okay. So you have one compositor,
Yep.
I noticed from the diagrams. So does that compositor do any visual work? Does it draw backgrounds? Does it draw any like top bars, bottom bars, any type of notifications or anything? And if it does so, does it display on both screens? And then how is that managed?
It depends on the product requirements. It is also possible to render some notification or some kind of launcher. So launcher can be, for example, implemented as a part of the compositor process. It can be also implemented as a separate value clients. Both are possible. It depends on the architecture we choose.
And then if you write it as part of the compositor, is it then considered, is drawing graphics onto two displays?
Yeah, that is also possible.
Yeah.
Yeah.
It's possible. Okay, so is that done? Sort of. Is there any product?
Yeah, for example, so for the demo, in the demo build we prepared in the booth, we have a notification UI. So in that notification UI, the notification UI can be seen in both displays together as per the current implementation. So yeah. Any other question?
Okay, so Thank you very, very much.
Yeah.